On the circles, let's not even multiply by pi, let's just keep the pi symbol there. Perimeter and area on each paper. Some of them calculated and not all of them to the area. On the first one, what was the perimeter? You add up all the sides. Not 8. 2 plus 4 plus 2 plus 4 should be 12. And the area of a rectangle is just base times height, so that was 8. Perimeter. Tanan, what'd you get for the perimeter on this? 18. And area?
12.
Nope. 3 times 6. Happened to also be 8. It's square centimeters, not just centimeters. Okay, perimeter, when you add up all the sides, 8 was what? 48. What is the 2 tick marks? What kind of unit? That's inches. And area, triangle is 1/2 base times height. So we come up with what? 96. That would be square inches. A smaller one is what? Abram, did you get that one? Perimeter? I didn't hear what you said. Did you say yes or no? So add up 3, 4, and 5. Show you what you have. L for the perimeter and the area. 6, because 4 times 3 is 12, but area is only half of that. 6 square inches. Okay, circles, circumference. Derek? And I'm going to just leave it 12 times pi because as we look at what we're going to do, the pi will cancel out. And how did he get that? One version of circumference is 2 times pi times the radius. So radius was 6 times 2 is 12, so 12 pi. 1 tick mark means feet. The area is pi times radius squared, so that would be 36 pi square feet. So same 2 calculations down here should give us 20 pi feet and 100 pi square feet. Any mistake I made? Okay, now what I want us to do is take a look at some ratios. We're going to compare the original sides, we're going to compare the perimeters, and we're going to compare the areas and see if all those ratios end up the same. So going back here, let's look at the sides. I'm going to kind of block it off. So when we compare the sides of one figure to the other, it was 2 to 3 or 4 to 6, which reduces to also be 2 to 3. So I'm going to just say that it is 2 to 3 in a reduced form. Let's compare the perimeters. The perimeters were 12 and 18. What's that reduced to? Divide them both by 6, which would be 2 to 3. Areas. Area was 8 compared to 18. Reduces to be. Divide by 2, which would be 4, 9. Okay. That's one example. Can't predict anything from one example. Let's look at triangles. In the sides, the ratio of the sides was 16 to 4, 12 to 3, or 20 to 5. What do those all reduce down to? Riley? What do they reduce to? What can you divide both of these by? Not 10, because you can't divide 5 by 10, go smaller. What is 20 divided by 5? We're just going to get 4. 4 to 1. Divide both of those by 5. Divide both of these by 3. Divide both of these by 4. So those all reduce 4 to 1. How about the perimeters? Perimeter of the first one was 48. The second one was 12. Ryan, what's 48 divided by 12 reduced to? 4 to 1. And the areas. Comparing 96 to 6. What's that reduced to be? How much? 16 to 1. Okay. Compare those numbers to like what we had the first time. One more example to look at. Early on in our class, we said you need at least 3 examples to look for a pattern. Okay. Right, on the circles, we really aren't comparing sides, but we're comparing the radius. So 6 to 10 reduces 3 to 5. Okay, circumference rather than perimeter. Okay, so that's 12 pi compared to 20 pi. So the pi's drop out. Divide them both by that and divide by 4, 3 to 5. And then the areas, some of you are predicting maybe. 36 pi compared to 100 pi. Again, the pi's divide out. 36 and 100 can both be divided by 4. That would be 9 and 25. Okay, what do you see as far as a pattern? What do you notice? Molly? If you multiply these 2 ratios, you get that ratio. Does that work in the others, or is it just the circles? It works in all of them? Okay. The area ratio. That is true. Another way to look at that is this area ratio would be 3 squared and 5 squared. So you could say rather than multiply those two, if you knew one of them, you could just square it. Now the theorem we're going to look at talks about this first ratio, not as the radius ratio, but as the similarity ratio. As the similarity ratio. As the similarity ratio. What was the similarity ratio and what we were doing the last few days? Similarity ratio is comparing the matching sides of the figures to see if they're in proportion. So if you know that ratio, you can figure out the other ones. So that's what our first theorem, or the only theorem in this section, is about. We did our investigation there on the board. Theorem 751 is called the proportional perimeters and areas theorem. It says if the similarity ratio of two figures is A to B, then the ratio of their perimeters is A to B. So notice we had the perimeter ratio was always the same as that similarity ratio. But then the ratio of their areas is the square of it. You can think of it as A squared over B squared, or just the AB ratio totally squared. So what we're going to do today is if I give you one of these ratios, you should be able to give me the other ratios. Then in a future lesson, we'll use it to do some calculating, like if we don't know something, how we can find the missing part. I guess, did I have that all written down? You don't have to write anything? You need an example maybe to go with it? Okay, so here would be what you can fill in your boxes with. Okay, you need the hypothesis of some kind of similar figures. So we've set up the 3, 4, 5 and doubled it to make 6, 8, 10 for right triangles for an example. So if this were your hypothesis, you have two similar figures. Doesn't matter what those figures are, as long as they're similar. The conclusion would be these are the ratios. Your similarity ratio would reduce to be 1 to 2. The perimeter ratio reduces to be 1 to 2. The area ratio is 1 squared to 2 squared, which is 1 to 4. There are some ways you can think about that, why that area ratio is squared. If you simply think about what kind of units there are on areas as opposed to perimeters or circumferences, the units on area are square units. So it takes a length and a width to create an area. So if you are doing the ratio of the sides twice, because you have to consider the length and the width, you're like multiplying those two ratios together. So perhaps you could tie the units on areas are squared, the ratio for areas is squared on what it was originally. And that might lead you to what we'll be doing when we get volume, what happens to the ratio there. So I'm going to give you a similarity ratio and have you give me the others, and then I think I'll see if I can give you an area ratio and give you the others. Switch the order of what I was doing. If you haven't checked out, the e-backpack has the PowerPoints on it. So she's looking at that to finish up some notes if I don't give you enough time to write them. All right, looks like we're ready. Okay, so if the similarity ratio of two similar polygons is 4 to 9, I'm giving you the similarity ratio, 4 to 9. I want you to write down what the area of the perimeters and the ratio of the perimeters and the ratio of the areas. How about grab your marker board so I can tell you that. Give two ratios in the right order. Ratio of perimeters, ratio of areas. top number, 4 times 4. Okay, the ratio of the perimeters is the very same as the ratio of the similarity, the ratio of the sides. But then the ratio of the areas is the square of that. So if you square the 4 and square the 9, you get 81. So 4 to 9 and 16 to 81. Now think what that is. That's if you really compare the two areas, what it reduces down to be. Okay, let's try this one. Two pentagons are similar. The perimeter of the smaller one is 20. The perimeter of the larger one is 50. So I'm giving you both perimeters. So which ratio can you figure out? Probably start with the, you can get to the similarity one, but first you'd rather better think about the perimeter one. Okay, so figure out what the ratio of the perimeters is. Compare the two perimeters and reduce it down. Okay, for anyone that didn't get done there, the perimeters, when you reduce 20 to 50, it reduces 2 to 5. That's the perimeter ratio. Similarity ratio is the same, and the ratio of the areas is the square of that. So 4 to 25. Right, now I don't have a different screen, but if I give you the ratio of areas as 9 to 25, can you tell me the similarity ratio and the perimeter ratio? So you're just square rooting. So 9, the square root of that, and the square root of 25. So we got 3 to 5 for the perimeters and 3 to 5 for the area, or for the sides. So keep in mind the similarity ratio is comparing what? Okay, like matching sides, matching radius, matching heights, whatever is matching up in those figures. Okay, so that's the theorem. So now what else are we going to do in the lesson? We're going to do indirect measurements. What's an indirect measurement? Well, it's a measurement you can't do directly. What would be some things you can't measure directly? Think of something that would be hard to take a tape measure and really measure.
A building.
Distance across a pond or something, a building, like the height of the building. Those are a couple examples that I'm using. So indirect measurement simply means it's a method that uses formulas. We use that quite a bit. Similar figures and or proportions to measure an object. So an example would be, let's try and find the width of a river. I have a real simple drawing here. Here's my river. Here's one nice straight bank, and then the other straight bank. So the water is in between here. I want to find how wide that river is. Now there are some things I could measure easily, and then some things that I can't. So let's look at, okay, this little triangle. Let's make it a nice 3, 4, 5 right triangle. I could measure that. Now what could I measure on the big triangle? It's hard to measure the width. It's also hard to measure the hypotenuse. Okay, you could maybe double it if this is the right length. but I don't know, looks like 4. I could walk this off or measure that, right? Let's say it's actually 21 feet. 3 feet, 4 feet, 5 feet, but when I go to that side of the river, it's 21 feet long. It's a lot bigger than doubled. I can use that information in order to find the width of the river. Are the two triangles similar? What kind of ways do we have for similarity? For triangles, there's either angle-angle similarity, side-side-side similarity, or side-angle-side similarity. So we've got to get these triangles similar before we can really go further. So talk to me about the similar triangles. It's angle-angle, tell me more.
Because you got a right angle and then you got vertical angles.
Okay, then we've got the vertical angles. Okay, so he's convinced me very quickly those are similar. So as we've been doing, you can set ratios of the matching sides. So the one we're interested in is W. W is going to match up with what side of this triangle that I did on the bank?
3.
The 3. Okay, so the W in a ratio with the 3, then 21 would be with the 4. So it's just similar triangles, applying it to something that might be a real life situation. So 63 divided by 4 is how much? 15.75. And we're doing a story here, so feet. So 15 3/4 of a foot. We will do some converting on some of these. Okay? So there's a width of a river type of example. What else did you tell me? Height of a building? Can't do height of a building very easily, so let's set one up related to that. Oops, let me go out. No, it's not yes. I think the touch thing is off. We'll get back to it. Okay, it's back. Just have to get the screen to cooperate with me. Hang on a second. Just going to back up, and I'll do it over here to get rid of the writing once my mouse shows up. Where's the mouse go to? That's what I wanted. Okay, I want to go back to this one. This is one way that you could measure like the height of a building or the height of a tree. This is my building. I can use a mirror type of example. Now the idea on the mirror one is the mirror would be placed on the ground, and then the person would be looking into the mirror and positioning themselves closer or further away so that when they look in the mirror they see the reflection of the top of the building. That's what's going on there. The person is going to be standing here, looking into the mirror, reflects up so that they position so that they see the height of the building. So you can find the height based on these similar triangles. Now, what information could we measure easily? How many of you are in physical science? Have you talked about this kind of thing with angle of reflection and angle of incidence? You've got angles. These are not vertical angles, but I think technically in physical science you talk about this angle and this angle being congruent, angle of incidence and angle of reflection. Based upon those being complementary to these other angles, you do get the two that are in our picture being congruent. That's a physics idea. So we do have similar triangles again by angle-angle similarity. What are measurements that we can find out easily? Tina? Height of the person. And technically I don't really care about the height here. I want the height to the eyes because that's what's forming the triangle. So to the eyes, let's make this a nice 5-foot height. Distance away from the mirror, let's say it's 6 feet. Then we can measure from the mirror to the building. that's gonna be quite a bit, let's say that's 30 feet. So how tall is the building? Calculate that and show me on your board. It's the height of this actual building. It's giving us some examples of how you can use similar triangles in real life situations. Units there. And is it inches, feet, yards, miles? What is it?
Feet.
You gotta have to line it. Check your multiply. What did you multiply? Units. Okay, a few more. That should have been 25 feet. No? Okay, how did you set that one up? The height of 5 feet would be compared to, the matching part of that triangle would be the H. And then the 6, the distance from the mirror, would be compared to that distance from the mirror. You look at the markings as far as the angles to see which sides are comparable. And then you just cross multiply, so it's like 150 divided by 6. Right, another type is, that time it worked nicely, shadows. We can use shadows to set up right triangles. This might be an example of finding the height of a tree, something like that. Okay, so let's make a real skinny tree here. And it's going to be measured at a perpendicular height. We're going to measure another thing at virtually the same spot. I kind of put them separate so that we can put the numbers in there easily. But maybe the height of a person, maybe the height of a yardstick or something like that. Let's just have a person again. Okay, so we've got that nice 5-foot person. And this time their shadow's a little bit longer, 7 feet. On the tree, what can we measure? It's shadow. Okay, the shadow's going to be on the ground. So this method, you'd have to have a nice surface in order to measure that shadow. Okay, that goes out quite a ways. Let's make it a nice number, 42 feet. How tall is the tree? Now, let's think about angles before you start in. What other angles are congruent and why? Where would the sun be in the picture? Yeah, kind of up this way. So the angle that's formed, you can either talk about the angle formed by the tree and the shadow angle. This angle would be the same as this one, as long as you're measuring them at virtually the same place and at virtually the same time. Because if you waited, if you measured the tree's shadow and then a half hour later you measured the person's shadow, what's happened in that time period with the sun? Sun's moved, so that's causing the angle to be different. So you have to do this method like at the same time, basically. Okay, so can you see the similar triangles again? And what ratios would we do in order to solve? This is come out a nice number. I'm giving you some nice numbers to calculate with for a little while. Tell me your ratio. Caleb, what are you using for your proportions?
5 over H.
You said 5 over H. 5 over H.
7 over
7 over 42. Anyone go H over 5, 42 over 7?
5 over 7, and H over 42.
Okay, now 5/7 and h/42 probably gives you the same answer, but look what you're comparing. Are you comparing similar triangles? If you compare 5 and 7, you're taking two sides of this triangle in comparison, which similarity compares one figure to the matching corresponding part in the other figure. So you're technically not following the theorem or the definition at all. It's a ratio that will give you the right solution, but it's not supported by anything. So be careful. Okay, so when you cross multiply, I think I saw 30 feet for the answer. Riley, get it? Okay. So there's a shadow type of example. Now let's make it a little bit harder for some follow-up ones here. Instead of just being 5 feet, this person's 5'9". And the shadow is 7'8". The telephone pole's shadow is 8'4", or 38'4", and I want to know the height in feet and inches for the telephone pole. So just forcing you to do some conversions here. So ideas, what would you do? Want to put them all into inches? Okay, that's one way to do it. That's why I put the bell ring problem. Okay, so can you convert those both to inches? The 5 feet times 12, and then add on your 9 more inches. Multiply your 7 times 12, add on 8 more inches. Yes, I hang on to that. Can you give me the answer in feet and in inches? If it's this many feet, can you figure out what that is in inches? And like the presented problem, so many feet, so many inches? Okay, we're getting a couple different answers, so let's see. 5'9" was how many inches? That was 69 inches. 7'8", how many? 92. 38'4" was how many inches? 460. And then we're trying to find h. Okay, so if you're agreeing on that, you're doing something like maybe 69 over h equals 92 over 460. Cross multiplied. (92h) equals, what's that? 740. Okay, then you divide it by 92. How much? 345? Okay, now 345 what? Okay, I've got inches. Now, if you talk to somebody and you were talking about that telephone pole out there, would you be talking about it being 345 inches? Probably not. You'd probably be talking about it as so many feet, maybe so many inches. So I want you to, I'm going to just force you to do something. I want you to get it back to a feet and inches, like the original problem started. So how many feet and how many inches? Not quite. Now, how do you figure that part out? And there's probably different thoughts going on. Should we?
We divide by 12.
Okay.
When you do it the other way, just like 5.9 over.
Okay, now be careful. 0.9 is not 9 inches. Inches are not out of 10.
Inches would be out of 12. So you would have to go 5 and 9/12 if you wanted to do that. Is that why you got a different answer?
Well, no, I got 29. I'm like, well, if they just want to round up, you could just do it that way.
Okay, don't do it that way because your decimals, inches would not be based on tenths, it would be based on 12ths. Okay. All right, let's hang on to your answers there a second. So you divided by 12 and got what number? 28.75, okay, feet. Now, I don't want feet in decimal, I want feet in inches. So now you can do this more than one way. Give me your thoughts. Megan, how did you do that? How'd you get 28 feet 9 inches? How'd you get that out of what I've got here? Or what did you do? Just kind of knew it was, like, what were you thinking of? Tell me.
Oh, no, it just clicked. It was like
Just
a-
clicked, you saw that number and you went, oh, 28 feet 9 inches.
3/4, and then you-
Okay, so she's thinking 3/4 of a foot, and maybe relating that to 12 inches. Okay, so she's got some numbers and some fractions going on. Dalton, listen.
28 times 12, and around 336, and times that from 345 and
Okay, so he's seeing, he knows it's gonna be 28 feet. He's seeing how many inches that takes care of. So he took that times 12 was how much? 336. So then he subtracted 345 and 336 and said, okay, there's 9 extra inches. So that's where he got 28 feet, 9 inches. Another thought, Julie?
Could you do like, 3, you know, it's 3/4, so 3/4, and then, x over 12, do you do it that way?
I don't know if that's what Megan really did or just thinking, but you were thinking 3/4 is how many 12ths? But yes, you can do it that way. And you can figure out when you cross multiply, that's gonna come out with your, I'm writing it wrong, 36 equals 4x. That will give you the 9 for the inches also. So there's more than one way to do that. But since the problem was presented in feet and inches, I wanted the answer in feet and inches. All right, I'm thinking yes. I think that that's our last example. Let's write down what we're going to work on after the quiz. Yep. Let me shut up my recording.
Where's the camera even at?
What's that?
Where's the camera even